So Nicolas is sort of a very interesting person. He's the director of the Department for Applied Physics in Geneva. And Nicolas does both theory and experiment. And he has done long-range teleportation experiments. I guess, oh, we're going to see here some pictures of that. Or
use that?
Yes. Doing, I guess, what are you doing here, Nicolas? CHSH experiments. And moreover, he has done experiments doing QKD and even make that into a company called IDQ. So in some sense, he is making real the things that Gilles Brassard thought of decades before. And moreover, Nicolas also is a theorist. So that's how I met him, talking to him about foundations and interesting questions about non-locality. And it's always been a fantastic pleasure working with Nicolas. And not only that, Nicolas also won a tremendous amount of prizes. He is owner of 2 ERC advanced grants, and he has the John Stuart Bell Prize and the Descartes Prize, and the list goes on and on. So that's also fantastic that we have you here, Nicolas. But maybe the most important thing is that you were president of the hockey club in, in Geneva, and this is another thing that we have in common. We also both love field hockey. And I read that your hockey club was voted Hockey Club of the Year by the European Hockey Federation in 2000. And in 2014, the first team won the Swiss champion for the first time in the century-long history of the club. So it's fantastic. Of course, Swiss hockey is not at all at the same level as Dutch hockey. But sorry. Anyway, without further ado, I give the stage to Nicolas. Thank you for coming.
Okay, well, thank you, Harry. Great pleasure to be here and hear all these nice stories that you tell. Yeah, so I put here some picture of Geneva and the Swiss Alps that you see on the back here. So this is an old experiment on Bell inequality that we did 20 years ago. So yeah, this is Alice, this is Bob. You know these guys, and in the middle you have some source, and this source is sending photons to Alice and Bob. And you analyze usually the contrast between the quantum predictions and then the observed experimental data contrasted with what you could do with classical local variables, very often called sheer randomness or just local hidden variables. And essentially you have 2 ways of presenting that or thinking about that. I guess physicists would mostly think that there is a source here that would, in addition to photons, also produce some local variables that are carried by these photons and propagate. You know, a copy goes to Bob and another copy goes to Alice. So they propagate along the optical fibers. Maybe a computer scientist or some other people may just think this shared randomness is kind of God-given. It comes from the top, or it has been created at the Big Bang and it is there forever, or since ever. And it makes no difference as long as we have only 2 parties, Alice and Bob. So both pictures are equivalent. But we want to go to networks, so more than 2 parties. And in these networks, we want still to test quantumness of these networks. And there we'll see that it makes a difference whether this shared randomness is kind of God-given since ever, or whether it really propagates from a source to the different parties. So in realistic networks, we'll see that on the next slide already, there are many independent sources. And so in this sense, this God-given view that everything was there since ever is not a natural view. The natural view is that all these many independent sources are kind of producing, in addition to what quantum mechanics predicts, some additional variables, and we want again to contrast the quantum predictions with the local predictions or the classical predictions. So here is an example of a network. You can have more complicated ones, but okay, something like that. And you'll see if there are, for instance, loops like that one here, and you may have endpoints. Maybe on the endpoints you can perform measurements. Here Bob would have to perform a measurement on, so this is one link. So maybe if it is quantum, you would have here some quantum stuff, maybe a qubit, here a qubit, part of an entangled state shared between Bob and Charlie, and maybe a further one here, shared with Florian, for instance. So this would be a free qubit or a free quantum stuff measurements. And I want now to analyze these kind of networks. First, in the case it is quantum. That's actually what people in this country and everywhere else in the world try now to develop in real life. So you put quantum states everywhere. And important is that these quantum states are independent. This one is maybe powered by solar power. This one is by nuclear power, and so on. And there's no reason to think that they are not independent. It's a very natural assumption. It is an assumption, but it's a very natural assumption that these things are independent. So this one would be the quantum network, and I want to contrast that with the case where we have independent. I want to keep the independence, but now classical shared randomness. So there's some shared randomness between Alice and Bob, shared by Alice and Bob, some other between Bob and Charlie, but independent. The probability distribution factorizes. That's the standard meaning of independence here. And actually I would also like to contrast all that with just having non-local boxes. I guess many of us, if not all of you, have heard of peer boxes, these kind of non-local boxes. But you see here, most of the players have no inputs, so it cannot really be a peer box in the usual sense where you always have inputs. So I don't know exactly what it means, but so the idea would be to look for and try to define and understand what would be non-local boxes for, boxes is meaning missing here, for networks. Still with the idea that this box should be independent from this box and so on. And it's not very clear what independence here mean again, but somehow you have a reservoir of boxes and you can plug them in. That's the intuition. And these boxes, they should satisfy what I call the NSI principle. Should be no signaling, have to define exactly what no signaling means, and independence. We have some intuition, let's be more precise. And I start with a very simple network, without loop, just ABC, and we have a source between Alice and Bob, another source between Bob and Charlie, and could be EPR source or quantum sources, and I want then to contrast that with the case when this one, Alice and Bob then share some randomness lambda 1, Bob and Charlie share randomness lambda 2, and these are independent. You just see the probability distribution of lambda 1, lambda 2 just factorizes. And then so I call these probabilities that can be mimicked by a classical model or a local model. I call them bilocal in this case, or two local because there are two sources. So it's a conditional probability of ABC given input x, y, z, and also given this value for the local variables. So Alice's outcome can only depend on the input and on lambda 1, while Bob can depend, so B can depend on y, lambda 1 and lambda 2, as here, and Charlie can depend on z, his input, and lambda 2, but no lambda 1 here and no lambda 2 here, because we don't have access to that. That's the intuition. And we would like something like a Bell inequality. Now there's a big difference with Bell inequalities, where the set of local Bell local correlations is a convex set, a polytope and this kind of stuff. Here, oh no, that's coming on the next slide. So here what I wanted to say, sorry, is that this NSI, no signaling and independence assumption or principle is as natural as the Bell locality assumption. And somehow you have seen it already and you have even made this assumption yourself when you were doing Bell inequality between Alice and Bob. Usually you would have that Alice gets an input and usually it is drawn from the top with a quantum random number generator. Okay, I put it on the left just to be closer in my drawing. So I have put a quantum random number generator here, which outputs a random, let's say, bit, which is usually considered as the input, and I ask Alice to also output this input. Of course, this x and that x should be the same. Similar on the other side. And this is now the standard Bell inequality scenario that we are very used to. But with the assumption that we also make in Bell inequalities, that this alpha, and clearly what is alpha? Well, it contains the information about the input, and beta contains the information about Bob's input. So alpha and beta, means Alice and Bob input, are independent of the local variable. And in the literature, this is named measurement independence. So we see that this idea of bilocality or trilocality, because we have three sources here, is something that we have been making since decades, since ever. Yeah, and now I come to this fact that the set of bilocal correlation, also trilocal, is not convex. And you can see that one possibility, one deterministic strategy is that Alice and Charlie, they systematically output 0. That's clearly a possible strategy. Another possible strategy is that they systematically output 1. However, you cannot mix these two. You cannot have that the first strategy happens with priority, let's say 1/2, and the second one also with priority 1/2. So you cannot mix them because Alice and Bob are independent. They don't share any randomness. So they cannot coordinate. And so the set of bilocal correlations is not convex, which makes everything much more difficult, but also much more interesting. And again, it's very natural. So here's an example where we have been able, and then I'll explain you later, we have been able to solve, okay, I don't give much details, but just to show you, the square is the set of, in this plane, okay, I'll tell you then what is this plane, but so in this two-dimensional slice of the polytope, the square is the set of local correlations, and this kind of star shape is the set of bilocal correlation. So of course, because of this additional assumption, the set becomes smaller. And you get these very nice inequalities. It's no longer linear, and this is not a plane, or it is not the intersection of a hyperplane with my two-dimensional slice. It's not a straight line here, so it cannot be a linear inequality, and clearly this is not a linear inequality. So what is it? So here I give you an example where everything is actually a binary. So the outputs are plus or minus ones, the input are 0 and 1s. And I introduce these two quantities, which are actually the axes of the graph I showed you on the previous slide. So here we fix y equals 0, and we define this parameter capital I. So Bob is always getting the input 0 here. We sum the statistics. We look at the statistics for Bob input equals 0. So these brackets is just the average value of the product of the outcomes, and we sum over x, y with these faces here. And then I do the addition on Alice's side explicitly. For J, it is almost the same, except that Bob input is 1. Do like that. And then let's look at here. So this variable, this local variable here, has to contain the information about Alice's output for both possible input values, x equals 0 and x equals 1. So actually you have an alpha 0 and an alpha 1. So if x is equal to 0, a will be equal to alpha 0. If x is equal to 1, a is equal to alpha 1. There's no other possibility. Must at least contain that. And now you can introduce the variable q, which is just the probability that alpha 0 is equal to alpha 1. So in this case, for this parameter I, if alpha 0 and alpha 1 are the same, then this average value is just alpha 0. And in the contrary, in the opposite case, which happens with probability 1 minus q, when alpha 0 is different from alpha 1, then they're just opposite, because it's just plus or minus ones. So this one would be 0, so there's nothing more. And for j, it is just the opposite. It's only with probability 1 minus q that they are different. Alpha 1 is different from alpha 0, and then it survives. So in kind of picture, we have put now Alice and Bob somehow together, and we are back into a more standard CHSH game. AB received the input Y, but the output, the product between alpha 0 and B. Charlie, no change for him. But now on this one, we can play the standard CHSH game. Here, you have the output on the left for input 0 times that, output for input 1 on AB times this coefficient. Usually you have a 2 there. I put it on the here, but it's the usual CHSH expression. And this one you can now write in terms of this I and j, I divided by q plus j divided by 1 minus q. And then whenever there is a q, of course q is a probability, so it has to be a number between 0 and 1, such that this inequality is satisfied, then you have a bilocal model. So actually this would be so minimizing over Q, this expression will give you the criterion, the inequality for bilocality. And here, okay, essentially you solve this, so you minimize, or you derive, you take the derivative with respect to Q, and this should be equal to 0, and a little bit of elementary algebra, and you get this inequality. So you get something. Nice. At least we get a non-linear inequality. Actually, don't have it here, but it's pretty old stuff, almost 10 years old. And I have to say, not much was found until recently on that. There's another paper, well, this is not so old, where we actually prove that indeed in this bilocality scenario and this inequality is so close to CHSH that all pure states and all states that violate CHSH would also violate the bilocality inequality. It's too close to CHSH, so it's not really us interesting, us what we would hope for. And also if we look at the critical visibility for this inequality, it is 1/2, so you may say, oh, this is much better than the critical visibility of CHSH, which is 1 over square root of 2. However, we have 2 singlets, or 2 quantum states. And so the critical visibility per singlet is not improved. It is still 1 over square root of 2. Again, disappointing. And so I'm going to present in this talk actually, I think, 5 challenges. So in case someone is looking for problems. Here's a first one, would be to find one of these bilocal scenario with just Alice, Bob, and Charlie. Bob in the middle is the standard entanglement swapping scenario, the most basic quantum network. But find such a scenario where the critical visibility per singlet is smaller than 1 over square root of 2. That must exist now because we make an additional assumption, this independence assumption. So that should exist. I have a very strong feeling that it exists, but we didn't find it yet.
You mean strictly smaller, I think.
Yes, strictly smaller. Sure, sorry. This is done. This is done here. Yeah, strictly smaller, correct. Thank you, Gilles. Okay, so still there is one thing which is nice with what I already presented here. You have no input, so you can start talking about non-locality without any inputs on the line. Actually, we could even go to longer lines and things like that. But let's look now at that. And one thing that Tobias Fritz did was a kind of easy observation, but okay, we don't have many results here. Take this random number generator and that one and take them from the side and pull them on the top. And then you get a triangle. You get both of them here, so they output X and Y, because these two now are together. So Alice and Bob, no change. And now you have a triangle, so you have a loop now. This is one thing that was so far missing. We had only straight lines. Now we have a loop, but this loop is just mimicking CHSH. It's CHSH in disguise. So it's not yet what we want. So we want a genuine triangle. So this is a problem on which I'm really spending a lot of time and talking to Harry each time I meet him and so on. And Renato has also to listen to all that and so on. And even Gilles. Okay, so we want something like that. And the question again here is there a quantum state, so feasible with quantum state, a quantum case feasible with quantum states and quantum measurements, which is not free local? Can these variables, alpha, beta, gamma, these local variables, be discrete? Or, of course, they could be continuous, a number between 0 and 1, a random number uniformly between 0 and 1. Can I make them discrete and finite? And here's an example which kind of is, I think, interesting. Let's suppose first that alpha, beta, gamma are uniformly distributed in the unit interval, and take as output function. So for Alice, for instance, the logical value beta is larger or equal to gamma. And similarly for Bob and Charlie. Then obviously the probability that all the three output 0, or actually I think it would be it should be a 1 here. That all the three output 1, so beta larger than gamma, gamma larger than alpha, and alpha larger than beta, that happens with probability 0. I know, so it's correct. So the probability that we are all equal is equal to 0. And the probability that for all the other cases is 1 over 6. And then if you look at that and you say, okay, now make alpha, beta, gamma finite alphabets, any size but finite, and add also the very natural assumption that the output function at Alice, Bob, and Charlie is the same. then you can prove that this is impossible. However, so at this point I was thinking you cannot discretize it. However, if you remove this assumption of identical output functions, then you can do it. You can reproduce this distribution with finite alphabets. And after that, in this paper, and that's mostly my former student Denis Rosset who found that actually if the outputs are bits, an alphabet of 6 letters is sufficient. On the other side, if you have quarts here, then you need 60 letters, but 60 is still a finite number. Now the other question here is, let's go this triangle. So the only thing that we have really access to here is this probability of ABC. There are no inputs, it's just outputs and you get ABC, a probability distribution of bits. It's about the simplest you can do if you have more than 2 parties. What does it mean here, no signaling and independence? If I give you a PABC, can you tell me it's signaling or signaling? Is it independence? What does it mean? It seems that we have some intuition, but at first sight, at least, it seems impossible to formalize. And somehow I find that quite fascinating. We have a kind of 6-qubit toy universe, now if we think in qubits, and we want to prove quantumness. Clearly, if I have quantum states everywhere, it must be more powerful than just having shared randomness. The intuition is there. And it should contain, if it is quantum, it should contain randomness. No, I should have here something that outputs randomness without any input. So it's not randomness amplification. It is purely outputting randomness without anything going in. But how can I quantify and even testify or witness that? So how to formalize this NSI principle? And I think there is one very good idea here, which I'd like to share with you. So there are no inputs, so no signaling. How can I formalize it? Well, Alice can do one thing. And if Alice does something, it's not going to change Bob Charlie's correlations. That's the idea of no signaling. What Alice could decide to do is not to do the measurement. She cannot do another measurement because there is no choice of measurement, but she can choose not to perform the measurement, or maybe she can also choose to change, where does it come now? To change the topology. Look at that. Alice, Bob, Charlie, but now Alice invited a friend, Dave, into the game. Now we have a square. But from Bob and Charlie's point of view, nothing has changed. Bob still has gamma coming in here, beta between Bob and Charlie. Charlie still has alpha coming here, still binary outcomes. Bob and Charlie didn't see any difference. So going from this triangle to this square should not affect the BC correlation. And here we really exploit no signaling. And of course we don't have to stop at squares, we can go to pentagon, hexagon, and so on. And moreover, in a square, Alice and Charlie, they're not connected, so they should be independent. The probability of A and C should factorize. And similarly, Bob, Dave are independent. Probability of B and D should factorize. So now we have no signaling and independence. Now we can start characterizing those probability distributions that satisfy the NSI principle. Well, here I still don't really tell you what I put here on. So alpha, beta, gamma is as before, but here something more. So let me start by making an assumption, which I will remove later, but just to give you make sure that you understand the basic idea. Let's assume that actually the distribution of the alphas or the betas or the gammas is all the same, and that the output functions are always the same. And then here I just put yet another copy of the same, still independent. In this way, I can do that. And I also make the easy assumption that the local single party expectation value is 0. So locally, you just get randomness. So output +1 and -1 are equally probable. And then I also, I already made the assumption that is everything the same. So AB, BC, CD, DA, the 2-party correlators are all the same, and I call it E2, the same for E3. And so again, no signaling means that the E2 of the square is the same as the E2 of the triangle, and the independence that I already mentioned before. Then you can write the PABCD of the square us up to normalization 1, so there's no single correlators. When you have the 2-party correlators all equal, the 3-party correlators all equal, and 4-party correlators of the square all the time. And when you compute these for the inputs as a choice of plus, minus, gives you that. You know also that E4 is upper bounded by 1, little bit of algebra, and you get that E2 is actually upper bounded by 1/2. So suddenly you get a constraint. And that's a constraint that was non-existing if you're just looking at a triangle, something more. And that was for the square. Okay, pentagon doesn't give you anything more, but if you go to an hexagon, and when it is a bit more complicated, it's not just a simple computation as I did, it's, okay, you have to add 12 of these inequality, positivity or non-negativity constraints like that. And if you add these 12 probably chosen, you get that actually E2 is smaller than square root of 2 minus 1. So 41% about, still under the assumption of E1 equals 0. And yes, and then you can actually, still under the assumption E1 equals 0, plot E3, but now it's the E3 of the triangle versus E2. And you get, so just the positivity conditions for the triangle gives you these lines here. So this is the kind of trivial thing. This is the NSI bound, which we just derived, expanding or inflating the triangle to an hexagon. And then once we had that, so everything here in should satisfy the NSI principle. And of course, being non-negative probabilities. And then we were looking for local models. And you just, well, use your computer and then you find local models everywhere except in this little zone here. This is not a straight line, it is indeed round. And what is here in? Well, we did enough numerical search that we are quite confident that there is no local model there, but we have no proof, and not even the slightest idea of how to prove that. Of course, we can do it with a computer and get confidence, but that's not a proof. And I have just zero idea how we could prove that there is no local model there. Presently, we're also looking for quantum point. If we find a quantum point here, then we open a bottle of champagne. That would be great. Good champagne, of course. So, of course, my second challenge is, well, is this region local? Did we just not look long enough to find a local model? Is there a quantum point there? We just don't know. So that's what we know about this triangle. No, I think there's one more thing I wanted to say with the triangle with binary outcomes. Now let's remove the symmetry. You know that all the states are the same, all the output functions are the same. Let's remove that. When you go from the triangle to the hexagon, what is nice is that between Alice and Bob, you had this, okay, now I call it here alpha. You can have another realization of the same variable between Dave and Eve. Okay, beta and beta prime, gamma and gamma prime. So you don't need to make an assumption that they are all the same because you just have enough to do from 3, it's 2 times 3 for the hexagon. And then you get this inequality, which I find very nice, by the way. Okay, but just to say that we don't need this symmetry assumption. We have also some results here. There's one thing that although this inequality is very nice, clearly there cannot be a 3-party correlators in that, because once we open the triangle, the 3-party correlator of the triangle is gone. And I have no idea how to involve 3-party correlators in my inequalities. There must be, of course, a 3-party correlation of a triangle must be important, cannot be not important. But I have just zero idea how one could involve that. So in no known examples, though, 3-party correlators appear. Only 2 parties, like here and here, the 2 parties, and the single parties. Okay, now let's go to 4 outcomes, because at the end of the day, we think that these are maybe quantum states, maybe 5+ states, and at the end of the talk, I'll show you some example with a 5+ state. And here we would say that because now it means if that is a 5+ state, that is a 5+ state, Alice holds 2 qubits, 5+ state of qubits. When Alice holds a 4-dimensional Hilbert space, so the natural number of outcomes is 4. But it's more complicated, 4 than 2. But still, let's try that. And the first thing you would try, of course, is Bell state measurement. You know, the one that we use for teleportation and these kind of things. Well, if you do that, it's easy to prove that PABC is local. Well, it's not good enough. Then you can even start with Bell state measurement that you rotate and things like that. Nothing like that works. So you need something else. You need other natural 2-qubit measurements. Of course, what is a natural 2-qubit measurement? Let me show you one which I think is quite natural and quite elegant. So we're looking for 4 partially entangled states, the 4 eigenstates of this measurement, which are of course mutually orthogonal. They all have the same degree of partial entanglement, because if they are fully entangled, it's again a Bell state measurement somehow. But so we want partial entanglement, and they should have some kind of the symmetry that you have for qubits. You recognize the Poincare sphere or the Bloch sphere. And one possibility is to have the vertices of this tetrahedron, call them M1 to M4, and have states which are superposition of along that vertex and minus that vertex, superposed with minus plus, with some coefficient C0 and Q0. And you have to choose these C0 and Q0 in order that they are mutually orthogonal. And if you impose that they are mutually orthogonal, also we have to be to form a basis, you get these numbers when they are orthogonal. So you get here an explicit 2-qubit measurement which has really all the symmetry, the natural symmetry of the qubits and things like that. I think it's interesting or nice in itself, but it's also interesting the kind of correlations that these quantum measurements predict. It tells you that, okay, the quantum computation just tells you that probability for ABC, whenever A is equal to B is equal to C, whether it is 1, 2, or 4, is this number. So relatively large, pretty large. On the contrary, if only 2 of them are equal and not but different from the third one, then you get a very small number, not 0, but quite small. And the rest of the case, you get this average number. So the third challenge, the fourth already, where was the third? Okay, is to prove whether this distribution is that local or not. It is quantum for sure by construction. It has all the symmetry one would expect from a quantum example, but we don't know yet whether this is local or non-local, despite quite some work done on it. Okay, so let me come now to the last part of my talk, where I have a positive answer. So at some point, we invited Professor Beji Salman, who is a professor of computer science in Tehran, in Iran. You know him, no, Harry? And very nice guy, doesn't drink alcohol, but besides that, he's absolutely fine. And which I told him about my triangle. Everybody that passed by in Geneva has to hear about that. And so he also had to hear, and he was very patient and was listening carefully. And okay, at the end of the visit, went back home. And a few months later, got an email with this example. So it's the first example of a genuine quantum distribution that is provably not local or not classical. And it goes like that. So first, all the states are 5+ states of 2 qubits. And the measurements are characterized by these eigenstates. So first you have 2 eigenstates for the 2, let's say the outcome 1 and 2. They are product states, 0, 1 and 1, 0. While the 2 other eigenstates are superpositions of 0, 0 and 1, 1. And you see that all this depends only on a single parameter, because S1 is S1 squared plus C1 squared is equal to 1, and this one has to be orthogonal to the previous one, so we have one parameter here characterizing these measurements. There's one thing which is, I think, pretty obvious. If let's suppose Alice gets that state, so the first result, so there's a 0 here, a 0 value for this qubit, and a 1 value for this qubit. Now let's suppose already a 1 comes here, so Bob cannot also get 0, 1. 0, 1, 0, 1 is impossible, but it could be 0, 1, 1, 0. However, now you have 2 zeros coming here, so you will never get 3 times one of these states. You get at most twice this state, and it would have to be the two different ones. You cannot even get one state twice. So actually this structure with this product state imposes a lot of constraints on local variables. You have a lot of probabilities that get exactly equal to 0, and that's always good when you want to prove something impossible. And here is the theorem by Salman. So if C1 is large enough, and actually so large that these states cannot be maximally entangled, they have to be partially entangled, it happens like that, then PABC is non-local in the sense you cannot write this free local decomposition here. And I'm not going to prove this theorem in detail here, but I want to give you a little bit of the idea. I already gave you a bit of the idea that this gives a lot of structure here. And indeed, you have two lemmas. The first lemma is really essentially exploiting that. And so in such a way that if I have now, Salman decided to label the local variables x, y, and z, and the capital X is the set of all the, what I call alpha, and the capital Y is the set of all the betas, and so on. And then each of these sets partition in two. So X is equal to the union of x0, x1, and also x0 intersection x1 is an empty set. The same for Y and Z. And it really goes like if for instance, Alice gets a beta that comes from this set Y0 and a gamma that comes from the set Z1, then for sure the outcome would be 0, 1. And if it's vice versa with the indices, you get the output 1, 0. And this is also true for Bob and Charlie. So you get all this structure and you get this here. And then this is one part of the proof. Then of course you have the constraint that all the probabilities of ABC, and you have 64, 3 to the power 3, no, 4 to the power 3, they must all be non-negative, and so these are inequalities that you have to exploit a bit, and I'm not going into the details, but at the end you get this second lemma. If C1 is larger than that number, don't exactly ask me where this number is coming from, but I would be able to reproduce the computation, but that doesn't mean I understand it. You have here a cubic root of something that involves the square root of 3, and then you put it here in this way, and you get a number. And then you can indeed, so this is a way of writing the positivity condition. Actually, the positivity condition is small or equal to that. And so if this is larger, then the local model cannot exist. Sorry? K is this. Okay, so we have now, and we are writing together, of course, with Salman this paper, but you cannot find it on the archive yet. Okay, so that is actually the status of my research on the triangle with all my challenges. And the fifth challenge is, for this one, so the very nice thing is that we have now a proof that there is a quantum triangle which is not classical. And we also know that the set of all three local models is closed. So if you have a point outside, well, outside is an open set, so you must have a little ball around these points, which is also not free local, but how large is this ball? What is the kind of robustness to noise? We have no idea. So maybe another challenge is to find how noise resistant or robust to noise the Salman distribution is. Okay, so these are again my 5 challenges. You're welcome to add some more. And yes, so thank you very much for your attention.
Some questions? Go ahead.
I feel like maybe I missed an important point, so I just thought I'd ask. You're trying to construct something which demonstrates non-locality without any choices in which measure you make each of these states. Can you elaborate on what the significance of that particular restriction is? I don't really understand.
Well, okay, so even in Bell inequality, we never have a guy there giving inputs. We put a machine that gives the inputs, so somehow if you include the machine into your settings, you also do Bell inequality without inputs. So in this sense, it's kind of not so original. But with my little, triangle, I want a loop, and a small loop is a triangle. So in this case, I find it very nice that you have this little universe. You don't put anything into it. You don't kind of probe it. It just runs by itself. Of course, it has to give you outcomes. If not, it's completely isolated. You can do nothing. It just gives you outcomes. And somehow, if you trust the assumption of NSI, no signaling and independence, you get quantumness out of it. So nature gives you the quantumness without you probing it. I just find that interesting by itself enough to deserve my time.
So one more question.
Oh yeah, just, but you mentioned also about making decisions about whether to measure or not. Does that not also constitute some?
Yes, but at the end, for instance, in the Salman example, you don't need that. But indeed, in the first, maybe the middle part of my presentation, I showed you that if we open this triangle, but we don't need to do it in reality. We just need to know that Alice could, in principle, open it, invite Dave and maybe more friends, and then we just impose positivity of probability. That's really nothing. Then we get actually restrictions on this E2, the two-party correlators. But then if we would go back to the triangle, and Alice just does some measurement, and we would observe, Alice, Bob, and Charlie do their measurements, and we would observe on the outcomes that this little 6-qubit universe would provide, we would observe a two-party correlation which is larger than this square root of 2 minus 1. We would know that something impossible has happened, or something signaling or independence has been violated.
Good. Maybe then let's finish this session. Thank you very much, Nicolas.